Hello, am I audible? Hello, am I audible?
হ্যাঁ,
Okay, and is my screen visible? Is my screen visible?
হ্যাঁ,
Okay, so how much did we proceed in the last class? I think we had four or five problems left in this section. Hello, hello. How much did we do in the last class? Can anyone remind me?
8 আর 8 হয়েছিল।
Okay, I think we should start from 9, no? Okay, so what does 9 say? Let T be an indefinite integral operator. T f x 0 to x ft dt on the space of continuous functions on the interval 0 to 1 is the space of polynomial functions invariant under T. If you integrate a polynomial, then you get a polynomial, na? So it is invariant under T. The space of differentiable functions, of course, if you integrate a differentiable function, you get a differentiable function. The space of functions which vanish at x equals to half. It is not true, na? Because if you integrate, say, 0 to x t minus half dt, what do you get? What do you get? It is t square by 2 minus half t plus some c, na? You get some constant, right? So that constant need not be 0. So integration, so this is not an invariant subspace under integration. This is not true. But the previous two are true. Okay, what about 10? Let A be a 3 cross 3 real matrix. Prove that if A is not similar over R to a triangular
আচ্ছা,
matrix.
ওটা তো ডিফাইনাইট ইন্টিগ্রেশন ছিল, মানে সিটা তো থাকবে না সেখানে।
Yes, but it is the antiderivative, na? It is the antiderivative, na? Okay, wait a minute. Okay, okay, I got your point. Yeah, he's right. He's right actually. It is a definite integral. So 2x. Okay. So this will be x square by 2 minus half x, right? This is 0, right? This vanishes at 0. You are right. You are right. Because the indefinite integral, it cannot be seen as a linear transformation, na? Then it becomes a multi-valued function, right? T has to send f to a particular function. I mean, yeah, you are right. So this vanishes as 0. So all of these are invariant under T. What about 10? What about 10? So let's see it this way. Suppose A be a 3 cross 3 matrix with real entries. Okay, now let f(ax) be the characteristic polynomial of A. So case 1, f(ax) has 3 real eigenvalues. Okay, say lambda 1, lambda 2, lambda 3 corresponding to the eigenvectors v1, v2, v3. That is, a vi is lambda I vi 1, 2, 3. Then a over this basis is lambda 1, lambda 2, lambda 3, where beta is v1, v2, v3, right? But a is not similar to but given a is not similar to any triangular matrix. Triangular matrix. So case 1 doesn't hold. Okay. So case 2. Okay. If x has one real eigenvalue. See, it can have one real eigenvalue or it can have 3, na? Can't have 2. And 2 complex eigenvalues, namely, what should I name them? Say a plus ib, a minus ib, right? Eigenvalue lambda. Thus, if x is x minus lambda into x minus a minus ib to x minus a plus ib over c. Thus, minimal polynomial of x, poly of a, is also fa, right? Because minimal polynomial should have all the roots, right? The which splits into different linear factors, which implies a is similar to a diagonal matrix over C. Okay, so 11. True or false? If the triangular matrix A is similar to a diagonal matrix, then A is already diagonal. Is that true? if a triangular matrix is similar to a diagonal matrix, does it invariably imply that A is already diagonal?
কি আবার বলো কোশ্চেনটা?
Question number 11. Think you have 1 minute. What can you say?
না, false এটা।
Counter example?
ওই 101 010 001।
Iki. What was your example, by the way? Just a minute. Yes, please.
101 010 001।
Hmm. Why?
Similar to identity, but not diagonal.
Hmm? Why is it similar to identity?
Sorry. I think the shape of the matrix is actually diagonal. I actually misunderstood the question. Sorry. Yeah, then it is true.
But you will have to come up with a proof still.
Because A is similar to a diagonal matrix, then there exists a basis such that a third bracket B is equals to B in the base is equals to some diagonal matrix. Then, with respect to some uh, change of basis, with respect to some basis, it is diagonal. So, mm, I think P A there exists some P such that P inverse is equals to D. So it is diagonal.
What is your A, by the way?
A is a matrix such that because of A is diagonal, we can say that there exists a basis B.
No.
Uh,
A is similar to a diagonal matrix.
yes,
Hmm. Okay. So you are saying that there exists P belongs to, say, M and R, or maybe M and F, such that PA there exists P belongs to MNF, that P not equal to 0, such that P inverse is D,
D.
right, which is
Yeah.
diagonal.
Uh,
Now what can we do? Can we do A is P inverse DP? Yes, but is P inverse DP diagonal? See, first of all, don't approach things this way, okay? You know that A is similar to a diagonal matrix, that is A is diagonalizable, na? Right? You know that already, right? If and only if minimum polynomial of A splits into distinct linear factors, that is true, right? Abhishek, right? We have proven it, right? So why can't we just take this? What is the minimal polynomial? X minus 1 into x minus 2, right? Isn't it? So this is similar to a diagonal matrix. This is diagonalizable, but the matrix itself is not diagonal. And you can create any such thing like a1, a2, dot dot an, okay, and put anything here. Just put anything here.
Actually, do
ai not
that
equal
in
to
my
az.
first counter example.
Then why did you not stick to it? Or to the stick করলি না কেন?
Actually, at first I understand it properly, but
Hmm.
after your counter question, I misunderstand the question again.
Yeah.
Actually, it's happened.
So what is the minimal polynomial here? That is x minus a1 to x minus an, right? Which doesn't have which has distinct linear factors, so it is diagonalizable. Okay, so let's move on to T. Okay, this is a very interesting problem. Just let T be linear operator on a finite dimensional vector space over an algebraically closed field F. Okay, let F be a polynomial over F. Prove that C is a characteristic value of Ft if and only if C equals to Ft for where T is a characteristic value of T. So first part is obvious, na? If Tv is equal to small tv, that is T is a characteristic polynomial of characteristic value of T, then we know that T to the power I of V becomes T to the power I of V, right? So from this we say that if f of T of is applied on V, we get f of small t applied on V, which implies f of T is a ch value of Ft, right? Now conversely, this is the main part, that suppose you take Ft and Ft has an eigenvalue, then Ft is of the form, I mean, and Ft has an eigenvalue C, then C is of the form Ft for t, some eigenvalue T of capital T. That is, I feel, very interesting. Take W equals to 0, be a T invariant, W equals to 0. Okay. W is a T invariant subspace of V, right? W is a T invariant subspace of V, na? That is true. V. Okay. Then we have seen that this set ST alpha W, that is all those Gx belongs to Fx such that G of T of alpha belongs to W. This is an ideal of Fx. We have seen that, right? Now let f of T of V is equal to C of V. Okay. Just a minute. I think there was something here. That lemma we used before. Something a lemma was used here. Some sort of lemma was here. Yeah. If alpha is not in W, there exists C belongs to. Alpha is not in W, there exists an eigenvalue C of eigenvalue C of T such that T minus Ci alpha is in W. So what can we say here? If T minus Ci of V is 0, okay, so we take Fx minus C, right? This polynomial. Okay, but so if alpha is an eigenvalue of ft with respect to eigenvector with respect to eigenvalue c, then f of t alpha is equal to c alpha, right? Which implies f of t minus ci of alpha is 0, right? This is true, na? This is true, na? So what does it mean? T satisfies. No, I mean, what I want to say is that f of t minus c, maybe I should write f of x. F of x minus c, this thing is in st alpha, na? Right? This thing is in st alpha, right? Right? But if you guys remember, to prove this, what did we go on to prove? We proved that I mean, what does this mean? What does this thing mean? If t minus ci alpha is in W, can we say that S t alpha W is basically generated by x minus c? Can we say this? Is it clear? Is that line clear to you guys? Hello? Is that line clear to you guys? Okay, tell me one thing. This is clear, na? That x minus c belongs to st alpha. This is clear, na? Since t minus ci alpha is in W, so by definition of this thing, x minus c is in this, right? But this is an ideal. But st alpha W is an ideal. And fx is a PID. Okay, let's write it this way. Into TIW. But by lemma, where was the lemma? Page number what? 203. Lemma page 202. But by the lemma, t minus small t I into alpha belongs to W for some ch value, characteristic value t of capital T. Thus, x minus t belongs to st alpha, which is an ideal in fx. But fx is a PID, huh? Fx is a PID means every, what should I say? Every ideal is principally generated. Since fx is PID, st alpha is generated by some hx, right? This implies hx divides x minus t. Since x minus t is in this, but degree x minus t is 1, that implies x minus t is hx, some constant, maybe a into x minus t. What we are trying to say is that st alpha is spanned by, is generated by x minus t. Thus x minus t divides fx minus c, since this is in ft alpha. Okay, thus ft is equal to c. Okay, so that was the proof. So you see, we are using this particular lemma. This I think you can prove yourself. I mean, this is not very tough. In cosine matrix, linear order, true or false. If A is diagonalizable, then T is diagonalizable. Try to find counter examples. Okay, these are not very tough. If you can't do it, then let me know. I hope you can take A equals to B and kill one. I mean, something like that. Find counter examples. Just find counter examples. A is diagonalizable. T is diagonalizable. Okay. Try this. I mean, this is just computation. If you can't do it, then let me know. Okay. No, 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 no. Okay. I will send you two alternative methods of 13 and 12. Okay. I'm sending you right away. Just a minute. Just a minute. Simultaneous triangulation. Give me 1 minute. I'm sending you some solutions. Wait a minute. Okay, so I am pasting the solutions I have sent you. Please have a look at them. Okay, I have sent it in the group. Please have a look at them. Then we will move on to the uh, next theory of the next chapter. Okay. I did the solution when I was a student. So, but you can look at your I mean WhatsApp actually. I have sent you. Then we will move on to simultaneous triangulation. Please have a look at them. You have 5 minutes. Please look at them. 5 to 6 minutes. Look at the solutions. I have sent it in the announcement group. Hmm. Oh. হ্যাঁ তারপর আরে না শুনছি ঠিকই Hello. So right now we are about to do simultaneous triangulation, simultaneous diagonalization. Okay, that means we will simultaneously diagonalize or triangulize a family of linear operators. I mean, with respect to same basis. Okay, suppose T1, T2, Tn be in linear transformations, we will try to find out a basis which will diagonalize or triangulize all of them. Okay. Okay, so let's go. Family of linear operators, we ask them, yeah, commuting family. Yeah. So let script f be a commuting family of triangulable linear operators. Okay, which means script f is a family of linear operators in which every linear operator in that family commute. Then ut equals to tu. Let W be a proper subspace of V which is invariant under F, that is, which is invariant under every linear transformation belong to F. There exists a vector alpha in V such that alpha is not in W, and for each T belongs to script F, the vector T alpha is in the subspace spanned by alpha and W. Clear? T alpha is in the subspace spanned by alpha and W. Let's look at the proof. Without loss of generality, assume that script F contains only a finite number of operators. Let T1 to Tr. Without loss of generality, because this thing MNF, this is a finite dimensional vector space. Okay, so it is enough to take a finite number of linear operators. Because of this observation, let T1 to Tr be maximal linearly independent subset of script F, that is a basis for the subspace spanned by F.
দাদা
Yeah.
তুমি মাইক অন করেছো?
Oh, I was speaking all along. Oh. Okay, so we are trying to triangulize or diagonalize a family of linear operators. We are trying to find a basis which will triangulize or diagonalize all the linear operators. Okay, so this is the statement of the lemma. We are trying to prove it. So without loss of generality, we can take script f to be finite. Basically since MNF has a finite dimension, so it is enough to take the linearly independent subset of f, which is maximal. That's what they have taken. If alpha is a vector such that B holds for Ti, then B will hold for every operator which is linear combination of T1 to Tr. Yeah, that is true. I mean, see, if Ti alpha is in this, okay, for I running from 1 to R, then you take any T which is a linear operator, which is a linear combination of these Ti's. So T alpha is nothing but Ci Ti alpha, but since each of them are in this, so their linear combination is also in this, so T alpha is in this. Okay, by the lemma before theorem 5, this lemma for a single operator, we find a vector beta 1 not in W1 and a scalar C1 such that T1 minus C1i beta 1 is in W. The one lemma we just used to solve problem 12. Okay, let V1 be the collection of all vectors beta in V such that T1 minus C1i beta is in W. Okay, see what they are doing. So first they have fixed W. Okay, W is fixed already. So for T1 they find C1 such C1 and beta C1 such that T1 minus C1I beta 1 is in W. Okay, now they are collecting all beta such that T1 minus C1I beta is in W. All those betas. Okay, this collection is non-empty because beta 1 is in there. They call this set V1. Okay, which is larger than W. This is larger than W now, because if you take W belongs to W, then T1W, C1W both are in W, because T1 because W is invariant under script F, that is invariant under T. So T1W minus C1W is in W, right? So W is a subset of V1. Furthermore, V1 is invariant under script F1. Okay, and they continue this process. Okay, so I will give you 2 minutes to finish the proof. Look at the proof. Hello. So have you completed it? Hello. So it is properly larger than W, right? V1, because beta 1 is in V1 and not in W. V1 is invariant under script F for this reason. Then yes, they commute for every t belongs to beta 1. That is t beta is in beta 1 for all beta is in V1. Okay, so that way yes. So that's how they go on to prove it. Now, now the very same thing for diagonalizability. For a dimensional vector space over F commuting with triangular operator, there exists an ordered basis V such that the operator in script F represented by a yes basis. Just algebraically closed field, there exists around singular matrix. I mean, just different version of the first theorem. Now they will prove theorem 7 for diagonalizable linear operators. Okay, this is simultaneous diagonalization. We could prove this theorem by adapting the lemma before 7 to the diagonalizable case. Just we adapted the lemma before theorem 5. But they will use induction. First, induction V equals to 1, nothing to prove. Assume the theorem for the vector spaces of dimension less than n, and let V be an n-dimensional space. Choose any t in F which is not a scalar multiple of the identity. Obtained by restricting the operators. Each operator restrict Fi is diagonalizable because it's normal polynomial device. So that is the proof. What's important is that if F is a commuting family of diagonalizable linear operators, I mean the statement, to me it's extremely unlikely. I mean, just because there is a commuting family of diagonalizable or triangulable linear operators, there exists a common basis which will diagonalize or triangularize all of them. I mean, it's highly non-trivial to me. So can we just solve the exercise today to before we can end the class? Okay, let's do that. So now see what they are doing. I mean, number one, so what is the technique? So technique is, first they try to find out uh, so let's do A. Or maybe let's do B. So you will see that this has eigenvalue 0 and 2. Okay. Okay. So if you do A V1 V2, it 0 V1 V2, you will find out V1 equals to minus V2. Okay. So 1 minus 1 is a CH vector of A corresponding to 0. Okay. Similarly, you will see that similarly 1 comma 1 is an eigenvector of A with respect to 2. So if you take beta to be 1 comma minus 1 and 1 comma 1, you get this. Now we will see whether this now we will check that whether this diagonalizes B or not. Okay, so let's see. We will try to write the matrix of B with respect to this basis. So B is 1A 1. Okay, so do B 1 minus 1. What you get? You get 1 minus A minus 1, which is 1 minus A into 1 minus 1. Okay. Similarly, B into 1 comma 1 will be 1 plus A into 1 comma 1. Thus you see P with respect to beta is 1 minus A 1 plus A. Okay. So beta is our required basis. You can try to do C. Let's look at 2. These are not very important problems. I mean, these are very computational, but not very important. Let T be a linear operator on an n-dimensional vector space. Suppose that T has an n characteristic values. Acha. Prove that any linear operator which commutes with T. This is a very important problem actually. Okay, so we will do 3. So let C1 to Cn be eigenvalues of T, all distinct. Okay, so n-dimensional space, so T v to v where dimension v is n. Okay, so we know that we can write v as a direct sum of these eigenspaces since T is diagonalizable. Let's take u v to v such that ut equals to tu. Okay, and alpha consider alpha I belongs to WCI. Okay, so one thing you can see is Tu alpha I, right? But what was Tu alpha I? So Tu alpha I is Ci alpha I, right? So U alpha I is an eigenvector of T with respect to Ci, that is U alpha I belongs to WCI, right? But what is WCI? But WCI is generated by alpha I, na? Because these are one-dimensional vector spaces, vector subspaces. Because there are This implies dimension V is summation dimension WCI, I running from 1 to n. This implies dimension WCI is of course 1, because the vector space dimension is n and there are n subspaces, every one non-trivial. Okay, thus you take U alpha I is basically nothing but some di alpha I, right? Okay. So can you write this? Can we write this? Can we write this? Tell me, can we write this? Hmm? Because for any because for any small vi belongs to WCI, U of vi, what do you get? I mean, what is this? T minus CI T minus CII plus DII of VI. What is it? TVI minus CIVI minus DIVI, right? But VI belongs to CI, so this is CIVI, so they cancel out, you get DIVI. Okay, only this. And we have seen that uh, alpha is a generator of WCI, and we have this alpha I belongs to D alpha I, where WCI is generated by alpha I. Okay, so VI, since it is in WCI, it is of the form some lambda alpha I, right? So UVI is U lambda alpha I, that is lambda U alpha I, that is U alpha is DI alpha I, so that is lambda DI alpha I, that is DI lambda alpha I equals to DIVI. Okay, so they are equal, right? So U restricted to WCI is same as TCI minus I plus DI minus I. Okay, so U is basically all their products, isn't it? U is basically all their products, na? Think as a block matrix. Understand? This is a polynomial in T, na? So U is f of T, where fx is product x minus ci plus di. You understand why this U is a product of these things? Do you guys understand why Vi is a product of these things? Think about U in a block. Okay. We have observed u in every basis element. Okay, so if you take v belongs to capital V, this v also is in this, right? So v is some summation lambda I alpha I, since WCIs are denoted by alpha I. Okay, so what is UVI? UV is summation lambda I U alpha I, right? That is summation lambda I DI alpha I, right? Right. And what is this? What does this product mean? Product T minus CII plus DII. If you applied this to V, product T minus CII plus DII of summation lambda I alpha I, what do you get? I think are all zero, right? There is a sum and there is a product, so we can, so this product, maybe I should write j here, and there is I running from 1 to n, j running from 1 to n. Only this term should survive. Just a minute. So what is this? T of CII plus DII acting over lambda j alpha j. What is that? I mean I not equal to j. What is that? If you apply it, lambda j T alpha j minus Ci lambda j alpha j plus Di lambda j alpha j. What is T lambda j alpha j? That is lambda j Cj alpha j minus Ci lambda j alpha j plus, wait a minute, I mean we have taken the product, we have taken the product to be block wise actually. Any v, just a minute. wait a minute.
হ্যালো।
হ্যাঁ বল।
হ্যাঁ, বলছি যে এই কোশ্চেন যেটা জিজ্ঞাসা করেছে সেটা হচ্ছে যে ওই commutes with t then this is a polynomial in t, এইটার মানেটা কি? পলিনোমিয়াল ইন টি মানে?
This means that u will be of this form, f of t, where fx belongs to capital Fx. Okay. So u will be of this form, a naught I plus a1 t dot dot dot, suppose a k t to the power k. Okay, of this form.
আচ্ছা,
No, actually I'm trying to explain this line. I mean, we have taken u to be this product, but the problem is that u restricted to that was it. I mean, how can we? This is not always, na. I mean, I'm trying to say, you understand the idea, na, basically. I mean, what they are doing is they say u is u restricted to WCI into and so on, u restricted to WCN. They are taking this product actually. Product u restricted to WCI. That's what they are taking. Okay. That's why this is they are product. I mean, doing product for the braces. Wait a minute. Let me see if there is any other. Try 5 at home. If you can't do it, then let me know. I will have to try it as well. Okay, we start direct sum decomposition next day. So this direct sum decomposition is 209 page. This is, I think, a big chapter. I mean, big section. No, not actually. So we can complete this chapter then the next class, and then exercise in the next class. Then invariant direct sums. So 15. There was one big section as far as I recall. Primary decomposition theorem. Probably this is the chapter. Yeah. Okay, that's it for today. Okay, that's it for today.